So far, we discussed two block ciphers, present and des. Now we are moving on to advanced encryption standard, and in short, it is called AES. So AES was actually chosen by a competition. So the original name of the algorithm was Randall, which is designed by John Damon and Vincent Raymond, two Belgian cryptographers. So they won the competition, advanced encryption competition, and this Randall became standardized in 2001 by NIST because it was the winner of the AES competition, and it's named AES. Of course, it is not exactly the same as with Randall, because Randall actually supports different block sizes, but NIST fixed it to 128 bits for AES. So there were other finalists in the competition, namely Serpent, Twofish, RC6, and Mars. These algorithms are also, as far as we know, secure. There are no cryptanalysis results that break these ciphers. So from time to time, they're used in real life, and they should appear in open source software like OpenSSL and so on. So the block size of AES is 128 bits. As I told before, Randall actually supports larger block sizes too. And the key length of this algorithm depends on the user. You have three choices: 128 bits, 192 bits, and 256 bits. So for personal use, we already talked about key lengths. This is enough. And for military use or for long-term security, it is good to use 256. And as far as I know, almost nobody uses 192 bits AES because it's somewhere in the middle. So people either choose 128 or 256. But if you have a special application where you need the key size to be this, maybe you can use it. The number of rounds depends actually the length of the key. If your key is shorter, like 128 bits, AES has 10 rounds. For 192 bits, you have 12 rounds. And for 256, the algorithm has 14 rounds. Because the key length increases, so you need more rounds to diffuse this key information to the whole cipher. This is why the number of rounds are increasing. And this is a substitution permutation network. Since its introduction, a lot of cryptanalysis results are obtained, but as far as we know, known attacks are ineffective. So this is why we use AES. And from Snowden documents, we see no indication that NSA can break AES. So we are assuming that there are also secrecy services has no way to break this cipher. So let's recall that a substitution permutation network looks simply like this. You have the secret key, and your key schedule algorithm provides you round keys. And at the beginning, you have an initial round, a round key layer, which is most of the time just XORing with the plain text. You have the substitution layer, permutation layer, and add round key. So this is your single round, and you repeat it many times. So AES actually in this form, but it has different representation. A 128-bit block of AES is divided into 4 words of 4 bytes. Each word can be seen as a row of a matrix. So this is the standard representation of AES. So instead of writing 128 bits, you are actually using a 4x4 matrix, which is actually consists of 16 bytes. So this is how we represent AES. So a single round of AES is actually like this. You have your round input. Again, is given as 4x4 matrix. So all of the boxes are actually a single byte. You have the add round key operation shown as AK. So here you are XORing round key with your input. And your round keys are also 128. So there's a simple XOR operation here. Then what you do is the substitution layer where you have sub-bytes layer. This is just application of an S-box operation for every byte. So this S-box is an 8x8 matrix. So every byte is put inside this S-box and put it in place next. So every byte is replaced with the output of the S-box here. So you are performing 16 S-box operations here. Next operation is shift rows. So you don't do anything to the first row. So this byte remains here. So also this 3 bytes also remains here. But for the first row, let's say, assuming that this is the 0th row, you rotate it 1 byte to the left. So this byte comes here, as shown as here, and this one at the end comes to the beginning, like here. So you shift the second row 2 bytes to the left and third row 3 bytes to the left. So this is why this column actually becomes a anti-diagonal. So this is part of the linear layer, but it is not enough because here you are introducing a diffusion at the row level, but you are not mixing columns. So for this reason, we have a matrix multiplication, which actually takes the input as columns. So you have 4 columns. You take, for instance, this column in this notation shown as C. It is multiplied with the matrix M, and the result is written to the same column. So you do the same for this column, this one, and this one. So this matrix multiplication layer is also operation is shown as MC. So this is your single round. So let's look at it in more detailed way. So first, let's talk about AES representation. A byte can be treated in 2 ways when dealing with AES. A byte can be viewed as a string of 8 bits. A byte can be viewed as an element of the Galois field GF2 to the 8. This is important because some operations are actually performed in the field. So we will see an example in a minute. So AES uses the Galois field defined by the irreducible polynomial given as this. If you are not familiar with finite fields, then it's okay. You don't need to understand this representation. But if you want to implement it, maybe you need to understand what is meant by a Galois field and how it works. A byte can be represented by a degree 7 polynomial where the bits of the byte corresponds to the coefficients of this polynomial. Now we can perform addition and multiplication on these polynomials modulo RP, which is this irreducible polynomial. This more mathematical representation is better to understand the security of the cipher. This is true. So let's look at the single round of AES. I briefly mentioned all of these layers, but now we will look at them in detail. So round function of AES contains the following 4 operations. Key addition, which is just XOR of the round key. Sub-bytes, which just uses a single S-box, but it takes input as a byte. And we have 16 bytes as an input. So you perform this S-box operation to the 16 bytes. Then you have shift row operation, which is just rotate to the left. And you have mixed column operation, which is just multiplication by the matrix M. The encryption operation, since this is a substitution permutation network, just the inverse of all of these operations. At the key addition, again, you XOR with the round key. In the sub-bytes, you perform the inverse of the S-box operation. At the shift rows, you rotate it to the right instead of left here. And for the mixed column, you multiply with the inverse of the matrix. But of course, maybe if you are using a mode of operation that turns the cipher into a stream cipher, then maybe you would not need this part. So this all will make sense when we talk about mode of operations in the next week. Okay. So let's look at the key schedule. I took this picture from the Block Cipher Companion book by Lars Knudsen and Matthew Robshaw. So this is how the key schedule for the 128-bit key works. So you write your 128-bit key here. So these actually rectangles represent 32 bits of words. So the rightmost 32-bit comes here. They are now represented as 4 bytes. they are shifted 1 byte to the left, as you can see here. Then these 4 bytes are, an S-box operation is applied to these 4 bytes. Then there is a round constant XOR here, only to this byte. Then it comes here. So this 32-bit word is modified, and it is XOR to the leftmost 32 bits. Then it is becomes the leftmost 32 bits again, but it is also XOR to this, XOR to this, and XOR to this, and so on. So this is just so this is your initial 128-bit key, and this is your so it is your actually first round key, and this becomes your second round key. For the third round key, you take this 128-bit value here and perform these operations, and so on. So this is how you perform the key schedule operation. So let's look at the layers in more detail. So we said that at first step, we perform the addition of round key. So this is your input of the round. Every byte is actually XOR to the byte of the key. So this is actually 128-bit value, and this is the 128-bit round key. You just XOR them. So there is nothing special here. It is just XOR of the whole block. Then you perform the S-box operation to every byte. So if you are performing it to this byte, it goes here. When you perform the S-box operation to this byte, it goes here. So this is the S-box of AES, and since it takes 8 bits input, there are 256 possible inputs and 256 possible outputs. So this table can be read like this. So if your input of your S-box is 3B in hexadecimal notation, you look at the third row and at the beat column. So this value says E2, so your output is E2. This is how you read this S-box. So it is just a simple table lookup. This S-box is chosen as the inversion of the input byte X when viewed as an element of the Galois field 2 to the 8. This S-box provides optimal resistance against linear and differential cryptanalysis. Actually, this is important because this is one of the best S-boxes for this dimension, which is 8 bits input and 8-bit output. So for an 8x8 S-box, this is something like the best we have in terms of security, of course. So it provides optimal resistance against linear and differential cryptanalysis. We will talk about this when we're talking about block cipher cryptanalysis, but we don't know if there is a better S-box that provides better resistance against differential cryptanalysis or linear cryptanalysis, because we will talk about differential or linear uniformity when we're talking about cryptanalysis, and we will mention why, what is the open problem here, and what is done so far. But if you can find a better S-box, it will be huge. Shift rows, as I told you, at first row, if we say the zeroed row, there is no shift here. Then first row shifted 1 byte to the left. As you can see, A10 goes here, A11 goes here, and so on. And the second row is shifted 2 bytes to the left, A22 comes here. And again, third row is shifted 3 bytes to the left, so A33 comes here, A21 goes here and comes to it here, and so on. So we are doing, I mean, the word is shift here, but actually we are performing a rotation. And finally, we are performing the mixed column operation, which is just a multiplication of columns with a matrix. So each column is multiplied with the same matrix and written here. So this provides diffusion at the column level. So if you look at the matrix in hexadecimal notation, it is given like this. But don't forget that this matrix multiplication operation is performed in the Galois field. So it is not just a regular multiplication. M is derived from the parity check matrix of a maximally distance separable code. This is these are called MDS codes. So it is chosen like this so that it provides a good diffusion. MDS codes are beyond the scope of this lecture because it is actually part of the coding theory. But AMP's feature about branch numbers is important for us because higher the branch number, the better the diffusion. So it is defined like this. So this is the matrix. And let's say that this is your column, one of your columns in, of the AES representation. So you're actually multiplying this row with this and obtaining a y0. You multiply the first row again with this and obtain the first value here, y1, and so on. So this is how matrix multiplication works. A matrix is called to have branch number beta if the above equality holds only when either all xi and yr are 0, or there are at least beta non-zero values among xi and yi. So matrix M has branch number 5, and it allows small changes to affect many bytes. This property provides better security against differential and linear cryptanalysis. So what does this mean? So what is this definition? So it works like this. So here we have the branch number 5. This means that, let's say that you have some column here, x0, x1, x2, x3, and you multiply it with your matrix and obtain these yi values. So if you only change one value here, x0 for instance, since the branch number is 5 and you are only modified 1, so 4 remains. So this means that the remaining, these 4 values has to change too. So this means that making a small change here affects whole column. So if you change 2 values here, in order to add it to 5, you end up with 3. So at least 3 of these values has to change. So branch number is important and higher is better in terms of security for diffusion. So this is why it is chosen. That, and in literature there are many studies for obtaining better MDS matrix than the one that is used here for AES. So since AES is the standard, and it has only 2 standards so far, which is triple DES and AES, skip check is allowed only for legacy use because it provides 80-bit security. So efficient AES implementations are successfully provided on many software and hardware platforms. So almost everywhere we can use AES. But sometimes for small devices or better powered devices, you might prefer to use a different algorithm which provides the same level of security in terms of bits, but which is kind of faster or requires less power and so on. So this is why we have lightweight cryptographic algorithms. So still lightweight block ciphers are necessary for constrained devices. But at the PC level, AES is like your best choice because AES instruction sets are available for CPUs. And I think since 2009 or 10, we have these CPUs designed by Intel and AMD. And the reason for is that USA made it a must for state officials to keep their hard drives always encrypted. So when a laptop is stolen or lost, government documents do not leak. So that was the main motivation for having full disk encryption all the time. But full disk encryption results in a 20 to 40% performance loss. Of course, depends on your CPU, and these numbers might change depending on your capacity of your laptop. But for this reason, CPU providers thought that it is a good idea to provide instruction sets for encryption. For this reason, Intel and AMD provided hardware-level AES instructions on their CPUs. And I think some ARM processors might having these instruction sets too, as far as I know. But almost every CPU manufactured by Intel and AMD since 2010 has these instruction sets. So this allows you to perform hardware level encryption, and every core of the CPU has these instructions. So you have very fast encryption at your CPU compared to your software implementations. This is very important. But of course, we cannot check if the manufacturer provided a backdoor to these implementations. So you have to use it at your own risk. So this concludes our discussion of AES, but I want to remind you two exercises I gave before to better understand the future topics that we are going to talk in a few weeks. First exercise was to think about the following problem. You are given a dice and you are allowed to roll it to see the result as many times as you want. You are asked to determine if the dice you have is a fair dice or it is biased dice which rolls 6 with probability 1/3 instead of 1/6. So what would you do? You're actually the answer to this question gives you the basic idea behind differential cryptanalysis. So we will talk about it in the future. And the second exercise was about hash collisions. Actually, it was about birthday paradox. How many people we need to have in a room so that we have two people with the same birthday with probability greater than 1/2. So the answer to this question actually gives us the background about birthday paradox, which is used in hash collisions. So security of hash functions actually can be measured by this answer to this question.